In our last lecture, we saw how life tables and survivorship curves provide us with different ways to organize and visualize information about demographic parameters, such as birth rates and death rates that influence population dynamics. The question is, how can we use this kind of information to explicitly model population growth? This is the question we're going to turn to in today's lecture. We'll begin by considering how we might model population growth under ideal conditions in an environment with unlimited resources. Then we'll turn to the problem about, we'll turn to looking at how populations grow when resources are limiting, which of course is more usually the case. Let's begin by going back to the hypothetical example that I gave you about the growth of a population of bacteria. Remember, I told you that if a single bacterium was left to its own devices and given unlimited resources, it would multiply so fast that within 36 hours its progeny would cover the entire surface of the Earth to a depth of a foot, and in a month it would fill the entire visible universe, and so forth. Now, of course, the key assumption here was that individuals in this bacterial population, all the descendants of the original bacterium, had no restrictions on their ability to gain access to energy and resources. This assumption generally is unrealistic, of course, although we'll see later that sometimes this assumption is met for a limited period of time in some populations. But nonetheless, this kind of population growth, when there are no limits, provides us with a good way to start to understand how we can model population growth in general. So that's where we're going to begin. Now, before we try to do this mathematically, I want to begin with a physical model to give you an intuitive feel for what you can accomplish with unrestricted population growth. Now, to follow along with this physical model, you'll need a piece of paper. Now, if I measure a typical piece of paper, I might come up with a value of a width of this paper of about 0.0025 inches. Very, very thin. You can measure this, by the way, by taking a ream of paper, say 500 sheets of paper, measuring the width of the whole ream, and then just dividing by the number of sheets that I know are in that ream. Now, what I want to do is use this piece of paper as a physical model for population growth by letting the width of the paper represent the size of the population. And I'm going to represent reproduction in this population by folding the paper. So, for example, if I fold the paper once, that would be like a bacterium reproducing once. There's now two of them, two thicknesses of that piece of paper, and I'd have an overall width of 0.005 inches. I've doubled the width, okay? After every generation, that is, after every time the individuals in this hypothetical population reproduce or divide again, we would fold the paper again to represent this. So, for example, after 2 generations, we'll have folded the piece of paper twice, first once, then another time, and the width of the piece of paper would be 0.01 inches, which would represent 4 individuals because it's 4 times 0.0025. You get the idea. So, what am I doing with this physical model? Well, at each generation, as I said, we're folding the paper, which is equivalent to multiplying the thickness of that paper by a constant factor. Namely, we're multiplying it by 2. And that's the equivalent of modeling population growth, where each individual in the population during a generation divides. Again, we're multiplying the population by 2 in each generation. Now, suppose I go back to the original unfolded sheet of paper, and then I fold it just 50 times. I'm going to fold it once, twice, 3 times, 4 times, and I'm going to just do that 50 times. In other words, what I'm doing is I'm modeling a population that is allowed to go through 50 generations, reproduce 50 times. That's all. Now, what would you guess would be the resulting thickness of the folded piece of paper? The answer is really quite amazing. After only 50 folds, the total thickness of this folded paper would be a lot more than I could possibly hold in my hand. In fact, it would be a lot more than could possibly fit in this room. In fact, it would be a lot more than I could possibly see from one end to the other. In fact, the thickness of this one paper, if I folded it just 50 times, would be 44 million miles. 44 million miles. Just to give you some scale of reference, that's almost halfway from the Earth to the Sun. That's a pretty thick set of folded paper. You can imagine the last few folds on that would be a little hard to do. Now, the point of this physical model is to give you an intuitive feel for the power of unrestricted reproduction. What we've done is model reproduction by doubling the size of the population each time, folding the paper each time. Now, if we worked out the calculations, if we represented this mathematically, what we really would see is that the width of the folded piece of paper after 50 folds would be 2 to the power of 50, 2 to the 50th, multiplied times the original width of the paper, which is 0.0025 inches. And if I work out the math, what it means is that after 50 generations, after 50 folds, the width of the paper would be about 2.8 times 10 to the 12th inches. If I divide through by 12 to get feet, divide through by 5,280 to get miles, I come up with 44 million miles. Why do we get such a big number? Well, it may not be intuitive to you because after all we're doing is doubling the size of the population each time. I mean, we're multiplying it times a constant. We're multiplying it times 2. But because the total number of individuals in the population is increasing with each generation, the thickness is increasing with each fold, we're multiplying a much larger number, an increasingly larger number, an accelerating larger number by this constant each time. And we can very quickly get a very large width of this folded paper, a huge size of a population. Well, actually, the physical model I just described to you isn't a very complete model of how populations grow. One problem with the model is that it assumes that each individual in this population simply adds one new individual. Now, that might be the way that bacteria reproduce, but that's not the way that most organisms reproduce. Another major problem is that the model assumes that no individuals ever die in this population. In other words, we're only adding individuals, none are ever dropping out of it. Clearly, we need to incorporate more information in our model to make it more realistic. Specifically, we need to incorporate more information about births and deaths. Now, what I'd like to do now is to walk you through the development of a more complete model of how populations grow when resources aren't limited. This model still will be imperfect. It will be imperfect because it will assume that populations can grow indefinitely. But as I said, it provides a good starting point for our thinking about how to develop such a formal model because it'll give us a way to explicitly add information about births and deaths to our calculation. Now, I'm going to describe some simple mathematics to you as I develop this model, and you might wish to sort of follow along on a piece of paper. I'll tell you what you might want to write down. Now, we might begin the simplest mathematical model of how a population changes in its size over time with an equation that goes like this. We'd write down n sub 1 equals n sub 0 plus b minus d plus I minus e. Now let me tell you what those various parameters that I've just described are. N I'm going to use to refer to the size of the population. And I've got two n's in here. I described n sub 1 and n sub 0. By that I mean the size of the population in the next generation. We'll let that be n sub 1. That's the left side of our equation. And the size of the population in the current generation. That's n sub 0. All right, so n sub 1 equals n sub 0 plus some things and minus some things. Now what we're adding to the right side of the equation is b, and we're going to use a capital B here, and I'll tell you why in just a little bit. But b refers to the number of individuals added to the population through births. So I'm going to add that number to the starting number, n sub 0. Now, I'm going to also add this parameter I. Now, I'm using that to indicate the number of individuals that immigrate into the population, the individuals that come from someplace else and join the population. Now, so of course, we're going to add b and add I on the right side of this equation because they're going to increase the number of individuals. We're also subtracting some things from the right side of the equation. We're subtracting capital D, and that stands for the number of individuals that die in some period of time. And we're going to subtract this capital E. Those are the number of individuals that emigrate out of the population, leave the population and go someplace else. So in English, the equation n sub 1 equals n sub 0 plus b minus d plus I minus e simply states that the size of a population in the next generation will be equal to the size of that population in the current generation plus all the individuals that have been added to the population by births and immigration minus all the individuals that have been added to or that have been subtracted from the population because of deaths and emigration. This is actually pretty straightforward. There's nothing complicated here. In fact, we can simplify this equation a little bit more, and we'll do that for the rest of this lecture by eliminating any reference to immigration and emigration. I mean, it's just another way of adding and subtracting individuals from the population. That can be important in the real world, but we'll simplify our problem by eliminating that. And so we might just write a simpler equation, which is n sub 1 equals n sub 0 plus b minus d. The size of a population in the next generation is the current size plus the number of individuals born in the generation minus the number of individuals that died in that time period of the generation. Now, what we're really interested in knowing, actually, is not the absolute size of a population, but the rate of change in the size of a population. The reason for this is that the significance of the absolute size of a population may be hard to interpret. I mean, consider the following example. Let's say we're interested in a population of whooping cranes. This is an endangered species that's breeding in Wood Buffalo National Park in Canada. That's actually the major breeding ground where the remaining whooping cranes live. And let's say that I told you that there were 198 individuals in this population, which is the number that were measured a few years ago. Is 198 individuals a sustainable population or not? Is this a good number or is it a bad number? Well, I don't know. I mean, for some populations, 198 may be a lot, and for others, it may not be very many. What we're really interested in is in knowing how that population is changing from one generation to the next. Is it increasing or is it decreasing? So what we really want our equation to describe is not the absolute number of individuals, but the rate of change in the number of individuals. And so we'd modify our equation a little bit by explicitly getting a factor of time in there. And we would write, for example, an equation that could look something like delta n over delta t. That would be the left side of the equation. All right? And the delta there is just a mathematical symbol that means change in. So the change in n, the change in number of individuals, divided by the change in time, in other words, by some time period, delta n over delta t equals capital B minus capital D. Now this is actually even simpler because what we've done is we've just simply said that the rate of change of the number of individuals in a population is going to be the number that are born in that population minus the number that die. Again, it's still pretty straightforward. But we still haven't quite gotten something that we can work with because for many populations, actually measuring the absolute number of individuals that are born or die in a population can be something that's very hard to do. Now, if we're actually working with a small population of, a couple of hundred whooping cranes, it's possible for us to actually count all the individuals that are born and all the individuals that die in a generation. But more often than not, we have to estimate births and deaths, and so it's more convenient to use the average rate of births and deaths per individual in the population, something that we'll refer to as the per capita birth rate and the per capita death rate. In this case, per capita means per head. So what we're really doing in this is we're using not absolute numbers of births and deaths, but the average number of births and deaths, the average proportion of births and deaths for particular kinds of individuals. Now these sorts of data, the per capita birth and death rates, are the kind of data that we can obtain from a life table, as we discussed in the last lecture. This approach allows us to generalize our model even more, since we can use these per capita death rates and per capita birth rates to express the numbers of births and deaths expected in a population of any size. And we could do that as follows. We'd write an equation that had on the left side of the equation delta n over delta t, and we put on the right side of the equation, say delta n over delta t equals small b times n minus small d times n. Now I've changed the b and the d to lowercase letters in this case, because what we're doing is we're not talking about absolute numbers of births and deaths, but birth and death rates. And we're multiplying those rates times the number of individuals that exist in a population at a particular time. So in English, this equation delta n over delta t equals small b n minus small d n really says the change in population size per unit time is equal to the birth rate of the average individual times the number of individuals in the population minus the death rate of the average individual times the number of individuals in the population. Now, there are a couple of more things that we want to do to this equation that we're developing to make it really useful. The first thing we can do is to rearrange those terms small b and small d, and we can gather them. It's really an algebraic rearrangement. In other words, if we know that delta n over delta t is equal to small b n minus small d n, we could rewrite that as saying delta n over delta t is equal to small b minus small d in parentheses taken as a factor times n. What we've really done is gathered the small d into a single term, small b minus small d. In fact, what this illustrates is that what's important here is not the birth rate, small b, or the death rate on their own, but the difference between the birth and the death rate, small b minus small d. And in fact, the next step would simply be to acknowledge that that difference, small b minus small d, is itself the term we're interested in. And we're going to call that term r. We'll use a small lowercase r here as well by convention. We call this parameter r, the difference between the per capita birth rate and the per capita death rate, we call that the per capita growth rate. So now we can actually write a fairly simple equation. We can simply write delta n over delta t, that's the left side of the equation, equals small r times n. Or in fact, if we wanted to use calculus notation, we would say dn dt. That's just the calculus way of saying a change in the size of the population per some unit time that allows us to consider infinitely small time periods. That's not an important detail, but we could say dn dt equals small r times n. And what that means in English is that the change in population size per unit time, that's the dn dt, equals the per capita growth rate times the present population size. That's that small r times n. Now, the point of developing this equation is that we now have a relatively simple relationship that gets to the gist of what we need to know in order to determine the future size of a population in terms of just two parameters: the present size of the population, which is what we've called n, and the per capita growth rate for that population, which is we called r. In fact, r, the difference between birth rate and death rate, is really what tells us most of what we need to know. If r is greater than 0, we know the population will increase over time, at least in our simple model. In other words, r will be a value that's greater than 0, so long as the birth rate is greater than the death rate. And if we multiply that times any n, we know that the number we're going to get is going to be a larger number. We're going to have a positive increase. Now, if r is equal to 0, the population will stay constant in size. In other words, the birth rate and the death rate are equal. So r is 0. And so we'll have no increase in the population over time. If r is less than 0, which happens if the death rate is greater than the birth rate, then we know that the population is going to decrease over time. Now, one last point I want to make in this equation dn dt equals rn is that if a population is living under some theoretical ideal condition, in other words, reproducing as fast as it can because it has unlimited resources, then we would refer to the r in this case as with the symbol r max. And we'd write an r with a little subscript max next to it. This r max we call the intrinsic rate of increase. And r max is really a kind of life history parameter on its own. What r max is saying what's the maximum rate that this population could possibly increase if nothing's getting into its way. And so we would write an equation for this maximum rate of increase as something like dn dt, dn over dt, equals r max times n, using explicitly the intrinsic rate of increase, but acknowledging that populations don't always grow at this maximum rate. Now, let's go beyond this mathematical equation and ask, what would it look like if we graphed this pattern of growth? What we would get is something we call exponential growth. And we call it exponential growth because a plot of a change in the population size over time gives us a kind of J-shaped curve. A J-shaped curve that's really characteristic of an exponential function in mathematics. Now, as an aside, I should tell you that we could develop a more complicated version of our exponential growth equation that actually explicitly had our intrinsic rate of increase as an exponent, which is why we get a mathematical, why we get a graph that's shaped like this. But that's a less intuitive way to do it, and it's not a detail I want to bother you with. Now, What we're plotting in this, I want to be explicit about this, is on the x-axis we're plotting time, a change in time. So we're looking at the population size over time. And on the y-axis we're simply plotting the size of the population. And if we have exponential growth, as is described by that equation, dn over dt equals r max times n, then what we would see is there would be a steady increase in the slope of the line. The population would increase, assuming r is a positive number. And the rate of increase of the population size overall would begin to rise dramatically. The slope would become steeper and steeper until eventually the line would almost be shooting straight up. Now, the rate at which we would have an increase in this line would depend on r. If we have a small positive r, then it may be that it takes quite some time before the line goes up and starts assuming an obvious J-shape. But if we have a high positive r, then we would see a much more rapid rise in the slope. For example, if we looked at this kind of plot for something like the bacteria that I've mentioned, we would see that the J-shaped curve would be apparent very quickly, right? Bacteria multiply very rapidly, and in fact, within a month, they would be filling the visible known universe. Well, how are they filling the visible known universe? Well, that's where this line eventually going to a steeper and steeper slope comes into play. That's how they do it. That's similar to the physical model we had when we were folding the piece of paper. With each generation, as time goes along, the rate at which the population size increases itself increases faster and faster. In fact, all organisms will eventually, if they're undergoing exponential growth, show a J-shaped curve. Take a pair of humans, for example. If you allowed a pair of humans to reproduce unchecked as fast as they possibly could, in fact, humans would eventually fill the known visible universe with human bodies. It would take them longer than bacteria. It would take about 4,000 years if you sort of calculate the estimates, but they'd eventually do it. This is what exponential growth is about. Now, it should be obvious to you from our discussion to this point that most organisms, in fact, don't undergo exponential growth. Or at least they don't for very long. In fact, the reason they don't is because they don't have the resources to do so. We know that now. On the other hand, some populations will undergo what's essentially exponential growth for a limited period of time. For example, if a new population is established in some new area with a small number of individuals, during the early growth of that population, we'll see effectively what's exponential growth, because there will be effectively no resource limitation for that small group. They'll multiply as fast as they can. Or another place where you see exponential growth is in cases where a relatively large population has become reduced because of some catastrophic event, for example, killing many of the individuals in the population. As that population recovers back up to a larger size, it'll undergo what is effectively exponential population growth. Now, the fact that populations can undergo exponential growth under some conditions brings more sharply into focus the question of how we would model the case when they don't actually undergo exponential growth. And most natural populations don't undergo exponential growth, or at least don't for a very long period of time, as I said. Instead, in most populations, what we observe instead is that as the size of a population increases, the observed growth rate of that population as a whole tends to decrease. That is, as the population increases in size, the rate of growth of that population becomes increasingly less than that's predicted by our exponential growth model. Now, the connection between the size of the population and its growth rate obviously has to do with the availability of resources. Because resources are generally finite, then there is generally some limit to the number of individuals that can fit into a particular space, that can occupy a particular habitat. This limit to the number of individuals that can fit into a particular habitat is what we call the carrying capacity of a habitat. And we denote it by the symbol capital K. Now, the intrinsic rate of increase of a species, R max, is a property of the species. It has to do with the life history characteristics of the species. K, the carrying capacity of a species in a habitat, is actually a property of the environment. It depends on the resources available in the environment. When a population's size begins to approach the carrying capacity of an environment, this will have a profound effect on the growth rate of the population overall. And this is because, very simply, individuals will not reproduce as much because they don't have as many resources available to do so, and individuals will start dying more because they don't have enough resources to maintain themselves. In other words, effectively what we see is that the per capita growth rate of the population begins to diminish. The population just simply doesn't grow as fast. Now, we can modify our formal mathematical model of population growth to incorporate this idea by actually adding a term that includes the carrying capacity. This model of population growth we call the logistic growth model. The logistic growth model basically is the same as the exponential growth model. Remember, exponential growth is dn over dt equals R max times n. Now let's multiply that equation by another term, and that term is going to be k minus n over k, the carrying capacity minus the number of individuals in the population divided by the carrying capacity. Now, I don't want to spend a lot of time on the mathematical details, but I want to tell you what this term that we've added to this equation, to the logistic growth equation, is doing. K minus n divided by k will approach 0 as a term as n, the size of the population, becomes closer to k, the carrying capacity, the total number of individuals in theory that can fit in the population, because k minus n over k becomes a smaller and smaller number as n increases. K minus n becomes closer to 0 as n approaches k. So by adding this expression k minus n over k to our equation, then what we've got is an expression that will become smaller and smaller as the population size increases, or as the population size approaches the carrying capacity. And because it becomes smaller and smaller, then the overall result of this equation, the equation now reads really dn over dt, change in population size over change in time, equals R times n multiplied times k minus n over k. The result of that equation will approach 0 as n approaches k. Now, if we look at this graphically, and this is the point we want to get to, then what we see is, instead of a J-shaped curve, again, we're looking at a graph of the size of the population over time, with time on the x-axis and population size on the y-axis, we would see a sort of an S-shaped curve. When the population size is low, then what we would see is that it would increase. It would start increasing with an increasing slope, sort of what we saw in exponential growth. But at some intermediate value, the slope would start to decrease again. And we wouldn't have a J shape to this curve, but instead an S shape, as that slope decreased more and more, and the height of the line approached, really as an asymptote, what the carrying capacity of a particular environment is. So we have then an S-shaped curve modeled by logistic growth that explicitly includes the idea that populations can't grow indefinitely, that instead the rate of population growth begins to tail off, begins to be reduced as the size of the population reaches whatever theoretical maximum size we think there is for that particular species in a particular environment. Well, we've now taken a quick look at two mathematical models we could use to describe the growth of populations of organisms. The exponential model provided us a way to explicitly incorporate information about birth rates and death rates in a way that helped us to characterize how birth and death rates affect population growth. We incorporated these two parameters into a single parameter, which we called R, the intrinsic rate of increase of a particular population. Now, the exponential model fell short for us because it assumed that the rate of population growth will continue to increase infinitely, because the population will never run out of resources, giving us astronomical growth rates, in theory at least, with a line that could essentially become straight up, representing something that is as improbable as bacteria filling the known visible universe. We know this can't happen. So what we did then was add a term to this equation to develop what we called the logistic growth model. And this term explicitly included the idea that there was some maximum population size, in theory at least, that could be reached. And it then added this term in a way that would effectively decrease the rate at which population size increases as the size of the population approached this so-called carrying capacity. Well, the question we want to turn to next is first to ask whether populations in nature or in the laboratory actually show logistic growth. And second, to ask what are the mechanisms that actually connect the carrying capacity to the growth rate of a population. In other words, what are the mechanisms that actually regulate population growth? And these are the issues we'll turn to in the next lecture.